I bet you're wondering, what is random block design and why is it important? Well, to be frank, random block design is just another one of those ways of using statistical techniques to make your job easier. It focuses on the idea of grouping similar factors in a way to perform a set of randomized tests. These groups are known as blocks and they intend to hold factors that each of the test subjects have in common. Basically known as homogeneous factors, these different things affect each group equally, making tests as fair as possible. It's all used to make equal conditions, which can lead to the most accurate outcomes. That's what this slide is supposed to depict, showing that a block is just equal to a combination of homogeneous factors. Okay, so you're probably asking yourself, what is the whole purpose of using randomized block design, and what is this slide supposed to emulate? Well, the goal really, or the point, is just to get rid of unknown variables, as illustrated by the eraser and the question mark y, x, and z. By creating unbiased groups and randomly testing them all under similar circumstances, we can minimize any bias that may occur in order to get the best and most realistic results possible. These results allow us to see which blocks will give us the best results or which will give us the worst. We are able to also take part in what's called analysis of variance, or AOV, being that randomized results may conclude that one subject acts the same no matter the circumstances, or it's based on the situation it's in. So I'm sure this seems easy enough, but I do want to make you guys aware of the pros and cons of random block design. My two resources being the textbook and the academic research paper known as statistical papers highlight some of the issues that comes along with it. One of the bigger things is that the absence of data is just the death of the random block design. This simply just means that the project or design only holds up if the data is validated. It's true that it can erase unknown factors and bias. However, if not clearly stated why results occur within the appropriate data, the right assumptions can't be made and more questions than answers become prevalent. So in doing this, I would just be sure and just try your best to make sure that when you're using this technique that everything is clear and easy to interpret so people can replicate your findings. So let's get into the engineering example. I'm going to use a stress test to block off three different metals and see how they will perform under a certain stress. We're going to use steel, copper, and aluminum. Basically, I'll give them all a set of homogeneous factors. These factors will include the same length of the metal for each one and the same thickness of each specimen. I'll also like to make sure they're tested in the same apparatus to get rid of any bias. From there, as depicted, I would just apply three different stresses of the same level randomly across all three different metals, just to see which breaks first and which breaks last, determining the strongest and weakest under the certain level of stress. From there, I can also complete analysis of variance as I try to come to the conclusion and identify any variance or correlation to the breaking of each metal. Does the breakage happen around the same time each test, or does that time for breakage vary heavily with the amount of force applied, is what I'm able to see now. If done right, randomized block design is just a simple way of seeing which of your test subjects performs the best under the situations you create.